How do you perform control system stability analysis? Imagine trying to keep a toy car balanced on a narrow beam. If it wobbles too much or tips over, it's unstable. In electrical engineering, we do something similar with control systems to see if they stay steady or fall apart. Control system stability analysis helps us understand if a system will keep working properly when disturbed. It checks if the output remains bounded when the input is bounded, and if the system can return to normal after a disturbance. This is vital for power converters, robots, and aircraft control systems. The first step is to look at the system's characteristic equation, which comes from its transfer function. This equation is a polynomial, and its roots are called poles. The location of these poles in the complex plane tells us if the system is stable. If all poles are in the left half of the plane, meaning they have negative real parts, the system is stable. If any poles are on the right half or on the imaginary axis, the system is unstable or marginally stable. One common way to analyze stability is the Routh-Hurwitz criterion. It uses the coefficients of the characteristic polynomial to build a table called the Routh array. By checking the signs of the first column, we can tell if any poles are in the right half plane. If all signs are positive and no changes occur, the system is stable. This method works well for linear time invariant systems and helps find the right gain values to keep the system stable. Another method is the Nyquist stability criterion. It involves plotting the open-loop transfer function on a frequency response graph called the Nyquist plot. By observing how this plot encircles a specific point in the complex plane, we can determine how many poles are unstable in the closed-loop system. This approach is especially useful for systems with feedback and complex dynamics. The Routh-Locus method is a graphical tool that shows how the closed-loop poles move as we change a system parameter, usually gain. By examining the Routh-Locus, we can see if the poles stay in the left half of the plane during gain variations. This helps us tune the gain to keep the system stable. Bode plots are another useful tool. They display how the system's gain and phase change with frequency. From these plots, we can find gain margin and phase margin, which tell us how close the system is to instability. Bode plots are popular because they give an intuitive view of stability and help in designing control systems. To perform the analysis, we start by defining the characteristic equation from the transfer function. Then, we choose one or more methods like Routh-Hurwitz, Nyquist, Routh-Locus, or Bode plots. Each method provides a different perspective on the pole locations or frequency response. For example, using Routh-Hurwitz, we arrange the polynomial coefficients in a table and look for sign changes. With Nyquist, we plot the open-loop response and count encirclements of the critical point. The Routh-Locus shows how poles move as gain varies. In real-world electrical engineering, stability analysis is used to make sure power supplies keep voltage steady, flight control systems respond safely, and robotic arms move smoothly. It guides engineers in designing, tuning, and validating systems to prevent oscillations or runaway responses. In summary, control system stability analysis involves examining where the poles are in the complex plane or how the system responds across frequencies. Using methods like Routh-Hurwitz, Nyquist, Routh-Locus, and Bode plots, engineers can confirm that systems will behave predictably and stay stable under different conditions.